Hi, did you know that the Earth's only natural satellite, aka our moon, is drifting away from Earth? That's right. The orbit of the moon is increasing in size by around 1.5 inches every year. In this episode, we'll try to throw light on more such interesting facts about the brightest object in the night sky and learn how its gravitational pull influences our lives on Earth. So, without any further ado, let's begin. Moon is Earth's only natural satellite. While some believe that it was captured by the Earth's gravitational force as it passed too close by, other scientists have suggested that it is a piece broken from our Earth itself. The latter theory became particularly popular when it was realized that the Moon is roughly the same size as that of the Pacific Ocean basin. However, that is not the case because we now know that the tectonic plate activity on Earth means that the Pacific basin has attained its current shape and size relatively recently and has little to do with how it may have looked 4 billion years ago, that is, when the Moon formed. Some scientists have suggested that the Moon formed from the material left over after the formation of Earth, or that Earth and Moon formed together as a binary system. But the problem with this assumption is that the Moon should also have had an iron core like the Earth, which it does not. So, the most acceptable idea regarding the formation of Moon is that a massive object hit Earth and broke away enough material from the Earth's crust and mantle which formed the Moon. This idea explains why the Earth and Moon have similar crusts, that is, the top solid layer on their surface. The lunar soil is in a layer ranging from 1 to 20 meters in depth. It is called regolith and is a combination of powder and broken rocky rubble. The regolith is a result of meteoritic bombardment, that is, a large number of small meteorites which would have burnt up in the Earth's atmosphere hitting the lunar surface. Larger meteor impacts have spread material around and mixed the stuff present on the surface in a given region. The lunar soil contains no water, but it has a high proportion of refractory or high melting point materials such as calcium, aluminium, and titanium. The rocks are all basalts, that is, they are a result of cooled lava, unlike the Earth, which has igneous as well as sedimentary rocks such as limestone and shale. The rocks contain some silicates as well as oxides of iron and titanium and some new materials which are not found on the Earth's surface. There are some differences between the Maria and the highlands also. While the Maria are basalts, the highland rock contains anorthosites, gabbro, and norites, which were probably cooled down slowly deep within the Moon. The composition of these rocks also vary because the Maria rocks contain more titanium, magnesium, and iron, while the highland rocks are rich in calcium and aluminium. The Maria rocks are aged between 3.1 to 3.8 billion years, but on the other hand, the highland rocks are much older at an estimated age of 3.9 to 4.5 billion years. Based on the age dating of the lunar rocks brought back by Apollo 17 and other missions to the Moon, scientists are convinced that the Moon formed some 4.5 billion years ago. Its surface then underwent extensive melting and chemical separation for the next 200 million years due to the large amount of heat generated by radioactivity and meteoritic bombardment. The bombardment probably stopped some 4 billion years ago, but the residual heat resulted in melting down to around 200 kilometers below the Moon's surface. From 3.1 to 3.8 billion years ago, lava rose up and filled the basins, creating the Maria. Since then, the Moon has been quiet except for the occasional meteor impact which may result in small quakes. The Moon has a very thin atmosphere called an exosphere, which is much less dense than the Earth's atmosphere. The exosphere primarily consists of noble gases like helium, neon, and argon with trace amounts of other elements. The low density of the lunar atmosphere and severe lack of erosion and volcanic activity implies that even footprints made by an Apollo astronaut or tracks of the rovers which land on the moon's surface will remain etched in the lunar surface for millions of years. The moon's core is 700 kilometers in radius, but scientists are not sure about its composition. The small quakes which are detected on Moon are 1 billionth the energy of a typical earthquake, and some of them are a result of meteor impacts. There also appears to be no magnetic field on the Moon, which suggests that its core is not molten unlike the Earth. However, some rocks do show evidence for a magnetic field in the past. Above the core in the Moon is a partly molten zone which is around 400 kilometers thick, and the deep quakes are thought to originate here. Above this mantle is a thin crust which is variable in thickness ranging from 0 to 65 kilometers. The early lunar spacecrafts indicated that the mass of the Moon is not uniformly distributed in a sphere, which means that there are mass concentrations called mass cons which have been detected beneath the circular maria such as Imperium, Chrysium, and Nectaris. It is believed that these could be a result of volcanic lava filling the basins. The fact that these concentrations have survived the 3 billion years since the basin filling suggests that the lunar interior is quite rigid, otherwise the mass cons would have sunk down a long time ago. The very first astronomical phenomena that comes to mind when we mention the Moon is an eclipse. A solar eclipse, as you know, happens when the Moon gets in the way of the Sun's light and casts its shadow on Earth. That means during the day, the Moon moves over the Sun and it gets dark. This total eclipse happens about every year and a half somewhere on Earth. A partial eclipse happens when the Moon does not completely cover the Sun, and that happens at least twice a year somewhere on Earth. But not everyone experiences every solar eclipse, so getting the chance to see a total solar eclipse is rare. The Moon's shadow on Earth is not very big, so only a small portion of places on Earth will see it. So you have to be on the sunny side of the planet and in the path of the Moon's shadow when this happens. On average, the same spot on Earth only gets to see a solar eclipse for a few minutes after every 375 years. But the total solar eclipse won't be visible forever, because the Moon's orbit is changing. In fact, the Moon's orbit grows about 1.5 inches larger every year. As the Moon's orbit takes it farther and farther away from the Earth, the Moon will appear smaller and smaller in our sky. This actually occasionally happens even now. The Moon's orbit is not perfectly round, which means that sometimes the Moon is slightly farther away from Earth than it is at other times. Sometimes the Moon is far enough away that it does not create a total solar eclipse. In this case, the Moon obscures most of the Sun, but a thin ring of the Sun remains visible around the Moon. But once the Moon's growing orbit takes it approximately 23,500 kilometers farther away from the Earth, it will always be too far away to completely cover the Sun. If the Moon's orbit keeps growing by only 1.5 inches every year, it will take more than 600 million years for total solar eclipses to completely disappear. On the other hand, a lunar eclipse occurs when the Earth comes in between the Sun and the Moon, such that the Earth's shadow falls on the Moon and it appears dark for some time. But it is worth asking then that since the Moon completes one orbit around the Earth in 27.3 days, or approximately a month, why don't we see a lunar eclipse every month? Well, the answer lies in the fact that the Moon is not orbiting the Earth in the same plane. In other words, the Moon's orbit around the Earth is tilted by around 5 degrees. This implies that even when Earth is aligned between Sun and Moon, it is still possible for the Moon to be illuminated by the Sun's light, which is what it is reflecting back to Earth. As a result, a lunar eclipse occurs 1 to 2 times and at most 3 times a year and no more. Because they don't happen every month, a lunar eclipse is a special event. But unlike solar eclipses, which are very rare, lots of people get to see the lunar eclipse. So if you live on the nighttime half of Earth when an eclipse happens, you will be able to see it. Another interesting fact about the Moon is that the same side of the Moon always faces the Earth. This is because the Moon completes one rotation on its axis in the same time it takes to complete one orbit around the Earth. As a result, we always see the same side called the near side of the Moon from Earth. The far side of the Moon, as shown in this picture, can only be observed by a spacecraft from a great distance. The far side of the Moon has more craters and fewer maria. It has also been found that it has a higher average altitude above the lunar average relative to the near side of the Moon. Many phenomena on Earth depend on the gravitational force exerted on it by the Sun and the Moon because the gravitational pull from them varies slightly from one region of Earth to the other. In general, any effect which depends on the difference between the gravitational forces on the opposite sides of an object is called a tidal effect. So, if we have an object with mass small m at a distance r from an object of mass capital M, the force on the object of mass small m is given by gmm by r square. So, if we move the object of mass small m, that will change the force acting on it. The rate of change of force with position dF by dr is equal to minus 2 gmm by r cube. This means that the change in force in going from r to r plus delta r is given as delta F, which is minus 2 gmm by r cubed multiplied by delta r. And the corresponding change in acceleration, denoted as delta A here, will be given as minus 2 gm by r cube into delta r. This implies that the tidal effect falls off as 1 by r cube instead of 1 by r square, that is, faster than the gravitational force itself. It is trivial to show that since the Sun is farther away from Earth relative to the Moon, the tidal effect due to the Sun is much weaker even though its gravitational force on Earth is stronger than the Moon. The tidal effects of the Sun and Moon are responsible for the ocean tides on Earth. In the rest frame of the Moon, the tidal effects on the center of the Earth is zero, while the tidal effect on the point closest to the Moon would be such that the water is pulled towards the Moon. Similarly, for the point farthest from the Moon, the tidal force will be such that the water in the oceans is pushed away from the Moon. This means that there will be a high tide on the side nearest to the Moon as well as on the side farthest from it. The Sun also produces a similar effect, but it is only half as great in size. When the Moon and Sun pull along the same line, the difference between the high and low tide is the greatest, and when they pull at right angles to each other, the difference between the high and low tides is the least. Actually, the height of the water tides is not found to be as large as one would calculate with simple assumptions because the Earth is not solid and is itself distorted by these tidal forces. This constant reshaping of the Earth helps to heat its interiors and dissipate the Moon's orbital energy. The Earth does not respond instantaneously to the tidal effects. Earth's rotation causes the bulge in the side near the Moon to get ahead of the Earth-Moon line. This means that the force can act to increase the Moon's orbital speed, which makes it move farther from the Earth. The corresponding force on the Earth causes its rotation to slow down, keeping the total angular momentum of the Earth-Moon system fixed. Similarly, the Earth exerts forces which distort the Moon. These forces acting on the distorted moon act to slow its rotation, producing a rotation period which is equal to the moon's orbital period. The tidal effects that the sun and moon exert on the distorted Earth produce a torque that results in a continuous change in the direction of the Earth's rotation. This motion is called precession and takes approximately 26,000 years to complete one cycle. Precession has important observational consequences. Since the Earth's axis is changing its orientation, its equatorial plane is doing the same. Therefore, the point at which the celestial equator and the ecliptic cross the vernal equinox changes its position in the sky. It has recently moved into the constellation of Aquarius. Remember that the Earth's tilt of 23.5 degrees does not change because of precession. It is just the direction in which the axis of tilt points. Since the vernal equinox is the starting point of the astronomical coordinate system of right ascension and declination, the position of all stars appear to change because of precession. It may seem like the change should be small since it takes 26,000 years to go through a full cycle, but it amounts to almost a quarter of a minute every year. Another consequence of this precession is that the Earth's axis will not always point directly at Polaris, the North Star. So, in this context, we can say that while the Earth influences the moon also controls the Earth. Do you agree? Don't forget to share your thoughts with us in the comment section below, and if you enjoy our videos, please like and subscribe to our channel and share our content with other astronomy enthusiasts. I hope you rediscovered our moon today and learned something new about it. I'll see you next week. Until then, take care.